Okay, good afternoon, everybody. We'll go ahead and get started since it's 12 o'clock. So last Friday's test I gave back last period. If you didn't pick it up, I brought them again today. You can come get it. It's pretty good feedback, should help you know kind of what's expected on a test. There's another test again this Friday. It's based on the lectures from Wednesday, Friday, Monday, so the 12th, the 13th, and the 16th. So the 3 lectures we covered since the last test will be kind of the upcoming one. So not the stuff from last class, but from Monday's class, the previous Friday and Wednesday. It'll be the same style, like a single question. When I wrote out the answer for it, and I tried to take my time and be nice and neat, it took me about 3 minutes and 40 seconds. So based on that, I figure the class should be able to do it in about 12 minutes. You know, 3.5 minutes for nice writing, and then extra time for thinking, getting stuff wrong, you know, going back, just stuff like that. It's easier for me to write out the answer, seeing as how I know the question, and I've been doing this for 30 years. So to that end, I am still going to give extra time, like I'll try and let it go up to 23 or 24 minutes. I think on Friday coming, it will be lecture and class. So I guess I care about what you think. Who would prefer to write it at the beginning and finish with a lecture? And who would prefer to start with a lecture and then do the quiz? Okay, so let me think about it, and then I'll kind of post on D2L what the format is we're going to do. I think that's everything. Any questions before we get started? For those keeping track of such things, today is the day of the strike vote for the month for members, so everybody is voting today. That strike will be tallied tonight, so you probably keep an eye on your email or the news to see if anything comes out. And like I said when we talked about it, a yes strike vote doesn't necessarily mean a strike happens immediately. It just means that's one of the options on the table, and they'll take time to decide what that's going to be. Okay, so last day we finished off Gauss's law, and we did a review of energy. We're going to start today by doing the electric potential of a continuous charge distribution. So that's where we're going to start today. So this is the question we'll do. And what we'll do is we'll follow more or less the same method we did with electric fields, but we won't follow it exactly because field and potential is not exactly the same thing. So we'll have the same concepts, but it won't look identical because we don't have to deal with the vector business. So we're going to say we have a rod with a length of 6 millimeters. For the sake of assigning symbols, we'll work in symbols for a while. I'm going to call that length L. It carries a net charge, 8.75 nanocoulombs. I'm going to call that Q. It's uniformly distributed along the length, so the same density of charge everywhere. We want to find the total electric potential, that's V, at point P, which is 1/2 of a millimeter from the rod. I'm going to call that bit X. Okay, so to stay with our method, what we'll do is we'll identify a small piece of charge on our rod. So that's a little teeny tiny element of charge. We'll label that dq. And what we know is that this small charge, dq, makes a small amount of potential. And that small amount of potential we call dV at point P. To get the net amount of potential, you have to find the amount of potential due to every dq and add them all up. And when we take a bunch of small things, adding means we do the integral. So the little bit of potential made by that little bit of charge is k times dq over r. As soon as we put r in our equations, we should put r on our diagram. R is the distance from the charge to the point. So there's R right there. Let's put a coordinate system in as well. We'll put the origin right down through the center of the rod. There's our x-axis. Our y-axis will go up through the center of the rod like this. And then our coordinate y will be from the origin to our element dq. Okay, are we all on the same page so far? Got everything labeled? You'll notice here I didn't draw dv. When it was electric fields, I had to draw dE because that was a vector. I could draw it with an arrow. I can't draw potential because it's not a vector, it's just a scalar, just like I can't draw temperature. Okay, so I don't draw anything here for this one. Okay, our total potential V is the sum of all the little v's, so the integral, k dq over r. Okay, I want to do an integral with respect to something, so I need to relate dq to the parameters of my problem. I see dq has a size of a little bit in the y direction, so dq has a length that we can call dy. Okay, so that's the physical size of it. If we relate it through charge density, the amount of charge dq is going to be the density times the length. And by density, we mean the linear charge density. It usually has a symbol of lambda. Density times length. So the density is lambda times my length dy. And over here on the side, we'll put our definition that lambda is the linear charge density. It would be the total charge divided by the total length. Okay, so when you write down a new parameter, you always do have to define that in your problem. Okay, so I see that my lambda's got a dy. It tells me I'm going to be integrating with respect to y. I have r here. I'd like to pull y into it. I recognize that r is the hypotenuse of a right-angled triangle, so r squared is x squared plus y squared. So r is going to be the square root of x squared plus y squared, or x squared plus y squared to the 1/2, whichever you like better. Okay, let's put these things together. I can take my k out front because it's a constant. Lambda dy over the square root of x squared plus y squared. Got another constant in there, lambda. I'm going to take that out front as well. You could write q over L here if you prefer. I think I'll just leave it as lambda, at least for a little while. So now I see I'm doing an integral with respect to y. I need the limits of my integral from y initial to y final. To pick the limits, you have to integrate, you have to sum up the charge over everything that has charge. So the charge is on the entire rod. So you have to integrate from one end of the rod to the other. So you have to go over the entire limits of the rod. So my y initial will be down here. The whole rod has length L, so from the middle to the bottom, it's going to put y initial at a coordinate of minus L over 2. My y final at the top of the rod will be at a coordinate of plus L over 2. Everybody okay with those limits? I know I posted it in the video, but I know it's easy to get distracted on a video, so if you have questions here, it's okay. Okie dokie, so y initial is minus L over 2, y final is plus L over 2. This integral right here, you have two choices. If your integrals are really fresh in your head, you can integrate it by yourself. Not so fresh in your head, you can look them up. On a test, I would give you a table of integrals. Outside of stuff like sine and cosine and power law, like I expect you to remember those. But these things, I don't expect you to remember those. Your math profs can worry about that bit. So k times lambda, that integral is the natural log of y plus the square root of x squared plus y squared. And that's going to be evaluated at plus L over 2 and minus L over 2. So next we put in our limits, we kind of neaten up our expression a little bit, and then we'll be finished with our equation for the potential. So k times lambda outside the natural log, L over 2 plus the square root of x squared plus L squared over 4. Subtract natural log of negative L over 2 plus square root x squared plus L squared over 4. When you get to this natural log business, probably you remember natural log of A minus natural log of B is the natural log of A divided by B. So that sort of thing we'll use a fair bit. So let's use that here. And we get that our total potential is K times lambda times the natural log of L over 2 plus square root of x squared plus L squared over 4 divided by minus L over 2 plus square root of x squared plus L over 4. Okay, so there's our equation for the potential. Any questions? Notice we didn't do any components, we didn't do cancellation. That's because it's a scalar and we don't have components and cancellation. So the question was, find the potential with the specific parameters. So we'll put our numbers in and we'll find what the potential is. So our values are that lambda is Q divided by L. Our charge is 8.75 times 10 to the minus 9 coulombs, divided by a length of 6 millimeters, so 6 times 10 to the minus 3 meters, gives us lambda of 1.46 times 10 to the minus 6 coulombs per meter. Our L, we just said, was 6 millimeters, and our X was 0.5 millimeters. Put all of that in our equation, and we should get a potential. I just don't want to write it all out. We should get a potential of 65,337 volts. I did do it a couple of times on my calculator. I'm fairly confident that I got it right, even though I'm bad for hitting numbers wrong on my calculator. Okay, any questions about that? So I thought it might be an interesting kind of review or comparison to compare this continuous line of charge to a discrete set of charges. So the next slide in the notes is a homework question where I have 7 charges, but all together they add up to the same amount of charge on that line. And they have a separation that means that they all add up to be 6 millimeters from top to bottom. So I think it's an interesting homework question to find the net potential due to this set of 7 charges. Compare what you get here to what you get here, and kind of, what do you think? Will it be close? Will it be bigger or smaller? Why would they be a little different? Should they be the same? So I think that would be an interesting homework question to do. I'll post the answers, and then we can talk about it, of course, if anybody has questions. Okay, so that was our line of charge. The next traditional thing to do is the ring of charge. So we're going to take a ring of charge. It has a uniform charge density. It's got a total radius of r and a net charge of q. So we take that ring, that line that we just had, and we just form it into a circle. Find the electric potential on the axis of the ring. That means we draw a line coming straight out for the center. We want the electric potential somewhere on that line. And then we're going to come and we're going to use our expression for the potential of the ring to find the potential of a disk. So that'll be part B. That's similar to what we followed with the electric field. And then something a little bit new is let's use our answers for A and B to find our electric fields. Okay, so that'll be our connection between potential and field, and see how that works. Okay, let's start with the ring. So we're going to start the same way. We identify a little bit of charge on our ring. We'll call that dq. Oh, maybe I should pick it up here because I've already got that one shaded in. Little bit of charge on our ring. So our little bit of charge, dq, makes a little bit of potential, dV, at point P, where dV is K times a little bit of charge divided by the distance between the charge and the point. So R is from our little bit of charge we identified to our point. There's our R right there. To find our total potential, we have to sum up all the little bits of potential. What will we put in for our R here? So from the center of the ring to the rim, that's the radius. From the center of the ring to our point P, that's a coordinate that we've called Z. So we put that one on the Z-axis. So R is the square root of Z squared plus R squared. So let's take our constants out front. K is a constant, so that can certainly come out front. Is R a constant, the radius of the ring? Yeah, radius of the ring is constant, that doesn't change. How about Z, our coordinate from the center to our point P? That's going to be the same no matter where DQ is. So if I pick my DQ here, 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 wherever I picked it on the ring, that value of Z would be exactly the same. So Z is a constant and the radius is constant. This denominator here can come in front of our integral. Sorry, that was just a little bit bad handwriting. Okay, so now this integral should be really easy to do. This integral means we sum up all the little bits of charge as we go around the ring. What will we get when we sum up all the little bits of charge? Q, we'll get the total charge, right? So when you add up all the little bits, you get the total charge to Q. So then our expression for our potential at point P is K times the net charge divided by the square root of Z squared plus R squared. Okay, questions? If you're remembering from the electric field, when we did the electric field, this was a bit harder, right? We had to think about all the cancellations and the symmetry, and we had to be a lot more careful there. This one turns out to be a fair bit easier. Okay, there's our ring. Now we'll take the idea from the ring and figure out the disk. So part B, use the expression for the ring to find the potential of a disk with radius R. So we still have our idea that we need an element of charge dq, which is going to make an element of potential dV at our point P, but we need to pick what our dq is. We need to pick a reasonable dq that's going to let us add up all the dq's over the entire thing. When I think about my disk, I see it as a sum of rings. So if I draw a little ring on my disk, if I take a small ring and bigger and bigger and bigger and bigger, eventually I can add up all of those rings, and in total, it would give me the entire disk covered by that set of rings. Okay, so a disk is a sum of rings. Therefore, dq is a ring. And makes potential dV. So let's think about the parameters of our ring. Let's say that it has a radius A. That's an A, and it's got a thickness dA. thickness is a very small thickness. Okay, so now we've followed our steps. We identified our dq. We thought about the parameters of the charge, dq, so the size parameters, just like we do with the electric field. So our potential, dV, is equal to our charge, or sorry, our constant K. We can use our result from the previous bit. So a ring has potential, K times the charge, divided by the square root of R squared plus Z squared. So a little bit of potential due to a little ring is going to be K times that little charge dQ, divided by the square root of Z squared plus R squared. So that's a small potential from the small ring. Oh, I went off the side, sorry. Okay, so we know the potential of a ring. We wrote that down. The amount of charge on our ring is dq instead of big Q, but otherwise we use the same result as before. Okay, are we still good? So now what we want to do to find our net potential, V, it's going to be the sum of all the little potentials, dV. So the sum of K times dQ over the square root of Z squared plus R squared. We have to think about what we're going to put in for dq, how much charge is on that little ring. So when we did our linear charge, we said that the amount of charge was the charge density times the length because it was a line. Here, this is a two-dimensional object, so our dq equals the area charge density times the area of that ring. Because the 2D object, we're using an area charge density. Our area charge density is sigma. Sigma would be the net charge divided by the net area. So there's our density sigma. The area of our ring, and I went through this in the lecture, the video I posted. So the area, if you think about it like it's a rectangle, it would be the length times the width. And if you wanted to picture it, if you take your solid ring, you snip it with a pair of scissors and you just unroll it, it would become a long rectangle. So the length of it is 2 pi times the radius, 2 pi a, and the thickness would be dA. Okay. I don't want to beat that to death since I did kind of go over it in the video. So then our area is equal to 2 pi times a times dA. Okay, let's put all this stuff together. Oh, and I made one goof. I'm so sorry. Back here on our previous slide, we better fix this before we go any further. The potential here due to this ring was K and Q. That part's okay, because here we used K and the amount of charge this time is dQ. Z is your coordinate to your point P, so Z is fine. R here is the radius of the ring, right? Here the radius of the ring has a symbol of A, so I goofed when I wrote an R squared here. That should have been an A squared because it stands for the radius of the ring. So I'm very sorry. If you're making notes, you should go ahead and fix that. Okay, now we're in good shape. Okay, we can plug our dq in, and then we can see about taking care of that integral. So v is the integral of k times dq over the square root of z squared plus a squared equals the integral k times sigma times 2 pi a times dA divided by the square root of z squared plus a squared. We can take our constants out front. K, sigma, 2 pi, those are all constants. A is a variable because we have to sum up all of our different size rings from the center to the outside. So A has to stay inside the integral. Okay, for our limits of our integral, we'll start right at the center where A equals 0. So that will be our initial. And we'll stop when we're out to the edge of the ring. So we'll stop when we get out here to the radius of the disk, which is where A is equal to R. Okay, this integral is a simple one. So we got K times sigma times 2 pi. That's just the square root of Z squared plus A squared. That's going to be evaluated at R and 0. K times sigma times 2 pi. Square root of Z squared plus R squared minus square root of Z squared plus 0 squared gives us K times sigma times 2 pi square root of Z squared plus R squared minus Z. So there's our potential of a ring. Okay, questions? Yep.
Sorry, I just can't see. What are the boundaries on the finished integral there? Is it R and A?
It starts at 0 and it stops at R.
Oh, okay.
Yeah. So for the next part of the problem, we're going to find the electric field of a disk and a ring from our potential. A sort of a typical problem in 2055, or kind of an electronics course, would be to do this problem. So often you can find the electric field by doing the integrals. Those are a little more complicated because of the vector nature. So often it's easier and better if you can to figure out the potential from the integral and then find the electric field, because to find the electric field we're just going to have to do a derivative. So we'll kind of go through that part next. And then I guess you can judge for yourself what's easy and what's not easy. So the next part is use your answers to A and B to find the electric field of a ring and a disk. So part C. So the first thing we have to do is figure out how we're going to do this. Part C, the electric field of a ring equals. Kind of the big deal that we're going to try and figure out here, and the important part to remember, is how do you find a vector from a scalar? The potential is a scalar, it doesn't have direction. Electric field is a vector, it does have direction. The way we do that is we remember that our electric field is the negative of, we call it the gradient, of the, oh my goodness, E is negative of the gradient of the potential. So this symbol right here, it just means that when we do the derivative, we have to think about the different components. So when we write this out in full form, it means that the electric field is minus the derivative of potential with respect to x in the x direction, minus the derivative of potential with respect to y in the y direction, minus the potential with respect to z in the z direction. So when you do the derivative with respect to x, that gives us our x component of electric field. With respect to y, gives us the y component, and z gives us the z component. So that's how you get the vector from the scalar. You do the derivative, and that gives you the different components of the field. Okay, good. Okay, so our answer for our electric potential of the ring, the potential was K times Q divided by Z squared plus R squared. Take the square root. So now we're going to do the derivative of that 3 times with respect to x, y, and z. Remember here, and I think everybody's seen this at this point, this means a partial derivative. So if I do the partial derivative with respect to x, x is the only variable, everything else is constant. So that's what that means. So my x component of my electric field, Ex is minus the derivative with respect to x. We see that there is no x at all in that expression. Everything in that expression is constant with respect to x, so the answer is 0. Okay, we can do it for the y direction as well. You can probably guess where this answer is going to be. That one's equal to 0 as well. So the electric field tells us how the potential changes with direction. And this is saying that it doesn't change in the x and y direction when we're looking at the potential on the axis. So that's what that's telling us. Okay, that leaves us with the z component. Ez is minus the derivative with respect to z. It's probably kind of funny, but I would say the biggest thing students do wrong with this problem is they drop the negative sign. Okay? Simple things to do, but make sure you kind of take care with those signs. You know, it's the difference between getting 95 on a test and 100, or the 100 is like way better. So constants come out front, minus kq times the derivative. People do derivatives in different ways. I know there's like some sort of division rule for the power laws and stuff. For the life of me, I can't remember it. So 1 over z squared plus r squared, the square root, is the same as z squared plus r squared to the negative 1/2. Everybody kind of okay with that? This is the way I'd rather do this derivative because I can remember this one and I can't remember the division one. If you rather do the division rule, then kind of fill your boots. It's fine by me. So I've got minus kq, I apply the power law here, so I've got minus 1/2 times z squared plus r squared. Gotta subtract a 1 from this one to get minus 3 over 2. And then my chain rule says I have to multiply by the derivative with respect to z of the stuff that's inside, so that'll be 2 times z. Okay. I know I said a bunch of steps versus writing them down, hopefully that's okay. Okay, so let's just make this look a little bit nicer. Minus times a minus gives us a plus. The 2's divide out. We've got k times q, and then I'm going to write this one in the denominator. Z squared plus r squared to 3 over 2. Okay, there's my z component. The last place people make a goof in this sort of problem, people don't seem to have trouble with the fundamental understanding. It's more the presentation of the answer, is that to finish your problem, you do have to write it as a vector. So the y and x components are 0, so we'll write the z components next to a k hat to give it as a vector. If you go back and we look at our notes when we found the electric field from doing the integral of a ring, this is what we got. So same answer, but we got it a different way. Okay, any questions? Okay, let's take this same idea and let's apply this concept to the disk. So we'll do the same thing, but we'll use the equation for the potential of a disk and find the electric field of the disk. Okay, so E of disk equals. So our potential for the disk, so we found that a few minutes ago. There was our expression for the potential of the disk, so we'll write that one down again. So for our x component, Ex is minus the derivative with respect to x that's equal to 0 because there's no x dependence of the potential. Likewise for the y. We can write those out quickly and get them out of the way. So x and y components are 0. The only component we'll have left will be the z component. We'll take our constants out front, so that's k, sigma, and 2 pi. They can go out front. And then we're doing the derivative of what's left inside. Square root of z squared plus r squared minus z. Okay, the derivative of this part is going to be z squared plus r squared to the minus 1/2 times 2z. Oh, I dropped my 1/2. Is everybody okay with this step? I just did that derivative in my head. So I multiplied the 1/2 down because the square root is 1/2 times the argument. You reduce the power by 1 and then do the derivative of the stuff inside. If anybody's got issues with that afterwards, just come up and see me and we'll kind of go through that step by step. And then the derivative of negative z is just going to be negative 1. So let's make this look a little more nice. And then the last thing we'll squeeze in while we're doing it, k is 1 over 4 pi epsilon naught. Okay, so we've got minus 1 over 4 pi epsilon naught times sigma times 2 pi times 1/2 times 1 over the square root z squared plus r squared times 2z minus 1. So let's see what cancels here. Pi divides into pi. 2 goes into 4, leaving 2 left over. 2 on top divides with this 2 right here. So that gives me minus sigma over epsilon naught z over z squared plus r squared minus 1. And then the very last step I'm going to do is just multiply that negative sign inside. Right? Rather than have it outside, I'll put it inside. And then we write our electric field as a vector, which is our very last step. Which is the same result that we got when we did the integral to find the electric field as a disk. Okay, any questions? Okay, so that's all uniform charge density stuff. We've got 10 minutes. I think that's going to get us through the next question, which is a non-uniform charge density. And again, if I lost anybody on the steps in that algebra, I know I went quick for some of them, just come see me afterwards and we can go through all those together. So the next one we're going to try is we're going to say with a uniform charge density, but we're going to make it an odd shape. So we put a couple of shapes together. So the wire here has a uniform charge density lambda, but we've got a long straight bit, and they're connected by half of a circle. I'm going to try and find the potential at the center of the circle. So let's get started with how we're going to treat this. I think this would be tricky to set up, pick a single DQ, find one set of parameters that apply it, and do one single integral. I think that would be a little bit dicey. What we could do instead is break it into 3 parts. So this can be section 1. That's going to make a potential here at this point. This can be section 2, which will make a potential here at this point. And this will be section 3, which will also make a potential at that point. If we find each of those 3 potentials and we add them up, we'll get the net potential. Okay, so I think this is going to be a more straightforward way to solve it. So V1 equals V2 equals V3 equals. I'm going to start with section 3. So let's find the potential due to section 3 first. So I'll draw that piece of the rod. The total length of that rod is 2 times r, because that's given in the picture. I'm going to put in my coordinate system, and I'm going to put in my point where I'm trying to find the potential. So I'll call that my x-axis. I'll call this my y-axis, and here's my point where I want to find the potential, my point P. I know that when I'm trying to find the potential, I have to identify a little bit of potential. I have to find the potential due to that little bit, and I have to sum them all up by doing the integral. So the first thing I'm going to do is identify my little bit of potential. My little bit of potential, I'll just take somewhere on that rod. I'll call that dq. The length of that little bit is a little bit in the x direction, dx. So my dq is equal to lambda times dx. The linear charge density times the length will give me the amount of charge. Let's get all of the values that I know on this picture. So from my point to the start of the rod, that distance is capital R. So this distance is R, this distance is 2R. From my origin to my dq, that's on the x-axis, so I can call that x. And when I do my electric potential dV, it's k dq over r. R is also between my point and my charge, so x and r are going to be the same thing. So I'll just put that in one line right there. Okay, everybody okay with the parameters? Okay, let's start finding the potential. So the potential due to section 3 is the sum of all the little bits of the potential, which is k times dq divided by r. dq is lambda times dx. R is the same as x because it's between the point and the charge, which is the distance on the x-axis. K times lambda inside of the integral of 1 over x dx. So I took my constants out front. This feels like a good time to figure out the limits of my integral. So I want to go from the start of my rod. So here's one end. That's my x initial. That's got a value of r. I want to go to the end of my rod. There's my x final. And that's got a distance from the origin of 3 times r. Is everybody okay with r and 3r? So my origin is at the center. The first end starts a distance r away. The final end is a distance 3r away. So my limits are from r to 3r. The integral of 1 over x is the natural log of x, evaluated at 3r and r. So I've got k times lambda times the natural log of 3r minus the natural log of r Do that division thing again. So my potential at 0.3 is K times lambda times the natural log of 3. Okay, so that simplifies to a very nice result. Questions? Okay, and then hopefully you can see the symmetry of the situation. This side of the picture looks exactly like this side of the picture. So section 1 is going to have the same amount of potential. Okay, if you wish to go through the process for a homework question, no problem. You can try it out, see that you get the same answer. But we can say by symmetry, because we love symmetry, V1 equals V3 equals K times lambda times the natural log of 3. Okay, that's sections 1 and 3 taken care of. To finish, we need to find the potential due to section 2. That'll give us some practice with doing the geometry of a circle. So my section 2 I've got my arc that looks like this. I'll draw it again so I don't have to go back to that big picture. There's my arc, looks like this. My point P is in the center. I'm going to pick my DQ to be a little piece right here. The distance from the center to here is the radius r, which we also call little r. So when we do our K DQ over r, that distance is from here to here, which is the radius of the circle. So my total potential, oh wait, let's deal with our DQ. So DQ is equal to lambda times the length. When we have a horizontal rod, that length is a little bit in x, it's dx. When we have a vertical rod, it's a little bit in y, that's dy. When we have a circle, it's a little bit of a circle, which is an arc length. So S is the arc length. And it's a little bit of the arc, so from here to here is our little bit of arc length ds. And then maybe not, you remember from high school geometry that an arc length is r times theta. That means a little bit of arc length is the radius times the little bit of angle d theta. Okay, so that's a little bit of geometry. Theta is going to be the thing that varies, so let's label this one as our theta right here. Okay, now we're ready to get going with our integral. V2 is the sum of all the little dv's, k dq over r, equals the integral k times lambda times r times d theta divided by r. So we see that those radii cancel. K and lambda come out front. Got the integral of d theta. So this is new. We're integrating with respect to the angle. We have to think about what our angles are. We start with our first dq down here. Our initial theta would be equal to 0. We go all the way around to over here. Our final angle would be pi. So we're integrating from 0 to pi. So that's k times lambda times theta evaluated at pi and 0. K lambda pi minus 0 equals k lambda pi. And then to get our net potential, we have to add them all up. So k times natural log of 3 plus k lambda pi plus k natural log 3. So our net potential then turns out to be k times lambda 2 natural log 3 plus pi. Okay, so that's what the potential due to that funny looking shape is. Okay, a few seconds left, but of course we'll quit there for today. And we'll do more potential in this relationship between potential and field when we're back on Friday. So it'll be like a half a lecture on Friday and a quiz on Friday, 2 things together.